Haskell while I was a postdoc in theoretical physics, and now I made the switch to software development and work at Infinipool, which is a Berlin-based software company, and we do data deduplication. And in this experience report, I'm going to give you a brief idea of what data deduplication actually is, and then tell you why we use Haskell and why it's a good idea for us. And then I'll go into some more details, into some aspects of the algorithms that we use in order to demonstrate how Haskell shines there. The idea of deduplication is best shown with an image as an example. So if you look at these Lego houses, then you will see that there are lots of repeating patterns. You have these arches and pillars, you have these windows, and you have these patterns of bricks in the walls. And if you look at the building instructions, then you will see that all these repetitions are explicit. So instead of writing put window parts here, put window parts here, put window parts here, they just write assemble 19 windows and place them at these points. And this is basically the idea of deduplication, to do this, not just for Lego building instructions, but for arbitrary data. So that's the idea behind data deduplication. It works across multiple files, so it's not just compressing a single file and then compressing the next, but it also detects similar patterns between different files. And the efficiency depends greatly on the kind of data that you have. So if there's data where there's just no repetitions, then you can't do anything with that. But there are certain kinds of data where it's very efficient. And the prime example is backup data, because if you imagine that you do a backup of your data today, and you do a backup of the same data, slightly changed tomorrow or next week, then there will be some parts that have changed, but most of it will actually be the same. And if you can detect most of the things that stay the same, you can really save a lot of space. And to give you some numbers, this is from one of our customers who's a genome research lab. They have to back up 200 terabytes of data, and our software allows them to cut this down to 40 terabytes, which saves them really large amounts of money. So basically, they can hire another PhD student for that, which is nice. So let's look at how this method works in a bit more detail. We have here streams of data represented by blocks of different color, and you probably see that there are these patterns that repeat. And in order for the computer to see this algorithmically, we first have to chunk the data up, and then we can see, okay, here's a chunk that agrees with that one. And then we have to save it only once and can reference it multiple times. Now let's look at what happens if we change the data slightly. Here in the second line, we have basically the same data, but we've inserted one brick at the beginning. And if we chunk this in the same way, then we see that indeed every chunk has changed. This is because the data has moved to the right, but the chunks haven't changed at all. So the image that we would like to have would be this one, that we have only one chunk that has changed, and the other ones stay the same. And you can do this by using something that's called content-aware chunking, that is not using a fixed length for your chunks, but by searching for some fixed but arbitrary patterns in your data, and then saying, okay, whenever I find one of these patterns, I end a chunk. And in this way, when you insert some data and your data moves, the chunks will move with it. And with this, you see that the data above and the data below that is very similar also has very similar chunks. So that's the idea. So why do we use Haskell? Or where do we use Haskell? We switched to Haskell for the default language for new projects last year. And so far, we have two programs that are implemented purely in Haskell. One is Tachometer, which just looks at your data and tells you how good it will perform with deduplication. So it chunks it up and estimates how many chunks are duplicates. And the other one is Autobahn, that performs deduplication for data that you store in the cloud. So at the moment at Amazon S3, and we're planning to add more backends for that. So why do we use Haskell? For me, especially with a background from theoretical physics, the main appeal is that you have a very high level of abstraction and are very close to mathematics. So if you have a problem that is mathematical in nature on the one hand side, and then you have a computer that you use to solve the problem on the other end of the spectrum, then it's very nice to have a language that is rather close to here. So you can talk about the problem and the solution that you want to have for the problem in the same language. And then you have a compiler that produces efficient code that the computer then can execute. And also another thing that's great about Haskell is that you have a lot of libraries that make your life very easy. I'll just highlight a few that we heavily use. Autoparsec, we use that for the chunking. It's a library that lets you write modular parsers that turn into very efficient code. Conduit we use to do processing of arbitrary large files in constant space. So it's a stream processing library. And Haskell is also a library that was very good for us. It was announced while we were starting to implement our program. And it's there to allow you to schedule requests to different data sources automatically. So you write your requests and perform computations with them. And the library basically analyzes automatically which requests depend on results from other requests. And then it can schedule all the requests that are not depending on each other in parallel to amortize your latency. And that was very useful. And there's other great libraries, QuickCheck, Servant, we'll have a talk about Servant and Haskell tomorrow as well. AWS for communicating with Amazon Web Services was very useful for us because that's what we do where we store our data. And there's many more. So now let me go into some depth into the algorithms that we use. And the goal of this is to show you how it is beneficial to work in a language that is rather mathematical. And the aspect that I want to go into is the deduplication of groups of chunks. So remember, we chunk our data and then we look for duplicates, but for efficiency reasons, it's not very good to work on the level of individual chunks because you want your chunks to be rather small because your chunk length is basically your unit of minimal change. As soon as you change one bit, you change at least one chunk. So you want your chunks to be small, but if your chunks are small, you have a lot of them and you don't want to send requests over the net for each individual chunk. So what you do is that you group consecutive chunks into groups. And then what you realize when you compare any two chunk groups is that there's basically two cases. Either a lot of the chunks agree from one chunk group to the other, or none of them do. And if you think about backup data, this is somehow intuitive, because if you have two chunk groups and you find there's some chunks that agree, then the most likely case is that they actually represent the same data, but slightly modified. And the likelihood for just accidentally having some few chunks in both groups, although they are unrelated, is really small because there's so many possible chunks. And this leads us to define similarity operations on chunk groups, where we say that two chunk groups are similar if they share a significant number of chunks. And this we will need for deduplication. And one thing that you can notice when you write this down is that this similarity actually defines an equivalence relation on the chunk groups. So just to remind you what an equivalence relation is, it's transitive. So if you have A and B are equivalent, B and C are equivalent, then A and C are equivalent. And it's also symmetric and reflexive. And every time you have some equivalence relation on a set, then it partitions your set into equivalence classes, where every equivalence class just consists of elements that are equivalent under this relation. So there's lots of examples for this. If you take the numbers modulo some number, then you can sort them in equivalence classes. And also here, these chunk groups are sorted in equivalence classes. How can you use this? Well, when you want to perform deduplication for some chunk group, so you have a repository that has a lot of chunk groups in it, and you have a new one that you want to enter there, then what you have to do is that you want to find chunks from this chunk group that are already in the repository. So what you do is that you look for a similar chunk group. So you can write a function, similar group, that takes a group of chunks, interacts with the repository, and then returns you a chunk group that is similar to it. And if you do this for two chunk groups that are similar to each other, then the result of this function will also be similar each time. So you can just take the same result for both requests because of the transitivity of the similarity. So this means that the equivalence relation that you have on chunk groups induces you an equivalence relation on the lookup requests themselves. And this notion, so what do we mean by equivalent requests? Well, two requests are equivalent if you know that they will yield the same result. And when you have multiple requests that are equivalent, you know they are equivalent, then you can just perform one of them and use the result for all of them. So that will save you a lot of work if you implement this. And we were able to quite easily extend the Haskell library by a function that is specialized for equivalent requests. And I'll just show you the type signatures of the functions involved. So this data fetch function is basically how you schedule requests in Haskell. You give it a request, and then the request is stored in some table and then performed at some later time. And it does caching and all kinds of things. And this function for equivalent requests basically takes the same arguments, but two additional arguments. One is the equivalence relation itself. So it takes two requests and tells you if they are equivalent. You have to provide this function. And then another one to get a canonical representative for any given equivalence class. So this is used to basically map all requests that are equal to some common key so that you don't accidentally perform multiple equivalent requests, which you don't want to do. So the exercise of this going into detail with this aspect was to just show you the importance of working with a language that has a high level of abstraction, because this helps you to see a bit more general patterns when you do concrete problems. And it's also quite easy to implement this here. We just need functions as values in order to control these equivalent requests. And that's basically it. I hope I have given you an idea about what we do, how it works, why we use Haskell, and then also demonstrate you a bit why it's nice for us to work with a language that has a high level of abstraction. And that brings you to my last slide, which actually my daughter has prepared for you. Thank you for your attention. By this relation. But if you have two that are equivalent, then they always have significant overlap. So at the borders, in principle, you partition your space into regions, and at the borders of the regions, there are chunk groups that do share some chunks, but they're not considered to be equivalent by our algorithm. But that's not really a problem, because we only need to find one chunk group that has significant overlap in order to do deduplication. Does that answer the question? To provide an API so that you can, the tool is a command line tool, but you can also run it in server mode, so to say, so that you can run it on your computer and then shuffle data over it via some HTTP connection, and then it puts it in the cloud. Yeah. One thing that is a difference to compression algorithms is that if I put some data in my repository today and some data tomorrow, then this will automatically detect the overlap. So if I did compression, then I would have to basically uncompress everything and then compress it together. One thing that I didn't mention is that you can also use it together with compression, so that when you have the chunks and you index them, then you can afterwards compress the individual chunks. So that also uses something. What you should not do is to first compress the data, because that will just scramble all your data and yeah.
Okay.
Yeah.
I think there was one more question.
Yeah. So our main customer is a software vendor that produces backup software, because that's the use case where you get most out of it.